Hi, this is Team LangLang, and welcome to our presentation. Next slide, please. The objective of our project is to identify language based off audio samples. The languages that we chose are Mandarin, English, and Persian because they're distinct enough to be considered in a classification problem. Automatic language identification is a core component of many speech recognition systems, as well as multilingual translation systems. Next slide, please. The major motivation of this project was that automatic language identification is a very useful concept, and it is a relatively new field, which makes learning more valuable. For example, Google Translate's detect language feature, it doesn't have an audio detect language feature. However, Apple's iTranslate app in 2020, it recently updated such that you can recognize language based off audio, which was fascinating. Additionally, it's a very marketable concept. For example, Amazon Transcribe converts speech into text, and this can be used to decode or note down customer service calls, or even be used for clinical documentation applications. Next slide, please.
So we collected our data from our friends and family, as well as online databases. In total, we had 500 audio samples for each language, and they are all 2.5 seconds long. Any audio that we find are less than 2.5 seconds are being repeated, and any audio that's longer than that will be cut. So we processed our data by running them through a volume normalizer and a bandpass filter. And we followed a loudness standard because we want to keep the volume levels consistent across all samples. We also filtered the signals to between 50 hertz and 8 kilohertz because that's around where the human vocal frequency range is, and it helps to eliminate some background noise. Next slide, please. Then we will convert the audio into MEL spectrograms as shown here, and they are 108 by 64 pixel images that we will be feeding into our models. We split our data into 60% training, 20% validation, and 20% test. And we also made sure that there's an equal distribution of languages in each data set and that no speaker would appear in multiple data sets. Next slide, please.
So one of the first models that we explored was the support vector machine. However, since it takes the data in a different form, we thought it might not be comparable to our final design. So instead, for the baseline, we pivoted to a multi-layer perceptron, and our final architecture involved 2 hidden layers, as well as some of the other hyperparameters shown. And for our final design, we decided to go with a convolutional neural network. And this was mainly motivated by the fact that we're doing an image classification problem. And our final architecture involved 2 convolutional layers and 2 fully connected layers. Next slide, please. In terms of the performance of our models, the MLP achieved a validation accuracy of 0.903, and the CNN achieved slightly higher 0.95. However, the main difference is the parameter size. And as you can see, the CNN is roughly 20 times smaller than the MLP. And this is because the CNN uses kernels and parameter sharing, so it has much fewer values to train. And this also led to a slightly lower training time. Next slide, please. In terms of qualitative results, on the left is a sample output for a batch of 20 samples, and highlighted in green are the model predictions. And as you can see, all the predictions are very high accuracy, and this can be attributed to the fact that our languages were chosen to be very different, which makes the classification task easy. And this is also reflected on the right in the confusion matrix, where along the main diagonal, we have the correct predictions with over 90% test accuracy. Next slide, please.
Overall, the CNN model exceeded the MLP model due to its higher accuracy as well as lower requirement in terms of memory. The most valuable learning experience from this project was the versatility of image classification, as it can even be used for audio classification problems. Some improvements when iterating this project again or doing it again include collecting more data with a more diversified set of speakers, possibly exploring other architectures, because I do know that some Facebook models use RNNs for their language translation systems, as well as exploring different parameters for spectrogram construction, as well as next time ensuring that audio samples are over 3 seconds in length, so we don't have to repeat the audio. Next slide, please.
And finally, as sort of an extension to our project, we decided to run the CNN on languages that we're not trained for. Specifically, we chose German, Arabic, and Japanese, and we took 10 samples of each from the same online databases. And the interesting thing to note is that the model predicted German as English 10 out of 10 times, but it would confuse between the other two languages. And this was somewhat expected because German and English are very similar languages, and a CNN works by detecting features in the data. And so we expect that similar languages will have higher accuracy predictions. And applications of this can be include transfer learning, because as demonstrated, the CNN is able to learn different features of the languages, so we can retrain the fully connected layers later on to adapt for other languages. And that concludes our presentation. Thank you.
Great, thank you. Oh, 12 seconds left. Thought you were going to run out of time. Great. Interesting. It's a tricky and interesting problem. I have a bunch of important questions. I got to get to them quickly. First of all, in your test set, did you separate out people into training, validation, and test set? Yes or no?
Yeah, we made sure that no speaker would appear in multiple data sets. So any speaker that is in validation, won't be in other ones.
Would not be in the other ones, right?
Yeah, would not be.
When you were discussing, that's great, that's important. When you were discussing these results, here you were quoting the validation results. You should never quote validation results. You should only quote test results. That's kind of the core lesson of assignment 3 or 4, when I finally introduced you to the 3 sets. The final test is data that the network has never been adjusted based on, and so I would urge you to get that right in your final report. It's the 0.913 and the 0.843, which is really the truth here, not the 0.95 and 0.903. And also, there's not 3 digits of accuracy there, so be careful with that. That's all I have for now. Ash?
Yeah, it was really good. I really enjoyed actually the investigation of German and English. That was a very, very good addition with your learning. In general, I would say, although like everyone here is involved with engineering concepts, it is useful to discuss the motivation behind why someone would say in your processing, use bandpass filtering and such, even if it's just straightforwardly to talk about how you want to get like the images from the sound. Yeah, great.
Yeah, I noticed that too. They mentioned the bandpass filter, and then they said filtered to be between 50 and 8 kilohertz. I assume that's what you did with the bandpass filter. Is that right? Because you said those two things separately.
Yeah, that's the bandpass.
Yeah, I would offer that joining that together would have made this presentation more efficient and more commentary on picking the right things to say and not spending too much time on things that don't matter in such a short presentation. That's a skill that you need to evolve, and maybe I'll add a few comments when I respond. Any comments from anyone else? Questions, suggestions, applause?
Could I ask what the MEL spectrogram is?
Right, so essentially, it's a different version of a spectrogram, which takes an audio sample and runs a fast Fourier transform of it to produce a frequency spectrum. So if you look at the images by columns, one column corresponds to one instant in time, and that corresponds to the frequency values. And across the width of the image is the duration of the sample. And a MEL spectrogram is just a nonlinear conversion to adapt for human voices based on regular spectrograms.
Okay, cool. Thank you, Max.
Any other questions? All right, let's move on to